In this video, we'll go over the answer key for Friday, April 24th. And what we're looking at here is more about batteries. And so we're going to start with this table, which is called a standard electrode potential table. So here we have a bunch of elements, bunch of half cells, and they're all being reduced. That is, all of these elements are being reduced. And we have a value next to them to tell us how much they want to be reduced. So things that have a positive value really want to gain electrons. Things that have a negative value really want to lose electrons. And the way that we got these numbers is that we created a battery where one half cell was always hydrogen and the other half cell was one of these elements, and we measured the voltage. We basically said hydrogen, the half cell, is always going to be 0. When we hook them up to these other elements, they get some voltage that's related to 0. And with this table, we can calculate the voltage of any battery as long as the half cell has a standard electrode potential to go with it. So let's see how we use that. And we're going to look at a battery that's made out of copper and zinc, which has our reduction potentials here. Now, when we calculate the voltage of a cell is equal to the cathode, the standard potential of the cathode, minus the standard potential of the anode. The cathode is where the reduction takes place, and the anode is where oxidation takes place. All right, so let's start with our first battery at the top. Zinc is going to zinc 2+. Since we're going more positive, we're losing electrons. If we're losing electrons, we're oxidized and we're our anode. And copper 2+ is going to copper solid. So we're going from a positive number to 0, which means we gained electrons. If we gained electrons, we're reduced and we're the cathode. So this is going to be copper minus zinc. Copper's 34 minus a negative 76, which is plus 76. This gives us a value of 1.10. If you get a positive voltage, that means this reaction is spontaneous. However, if we flip the battery around and copper is now oxidized and zinc is now reduced, now when we do our calculation, zinc is going to be our cathode, copper is going to be our anode. We now get a negative number. So if you get a negative voltage, that means your battery as hooked up is not spontaneous. So let's determine if the batteries shown here and the reactions shown here are spontaneous. So we have a nickel and zinc battery. Nickel is going to nickel 2+. Therefore, it is going to be oxidized because it's losing electrons. Zinc is going from 2+ to 0. That means it's gaining negative charge, which is reduced. So nickel is our anode, zinc is our cathode. Cathode minus anode gives us a value of negative 0.53, not spontaneous. I'm getting the negative 0.76 and negative 0.23 from our standard potential table right here in the problem. Now we can also use our standard potential table to determine if acids will dissolve metals or not, because not all metals dissolve in acids. Basically, any metal that is below the table or below hydrogen will dissolve in acid. So basically, any metal that has a negative standard reduction potential dissolves in acid. Any metal that has a positive standard reduction potential does not dissolve in acid. So here I have A and B. So we have aluminum. Aluminum has a negative reduction potential, so it will dissolve in acid. And now, since we have something that dissolves in acid, we need to write the balanced redox reaction. So for hydrogen, the starting redox reaction is always the same for hydrogen. is 2 hydrogen ions plus 2 electrons go to hydrogen gas, H2. For metals, you have to determine what charge they will go from the periodic table. This is something that we covered extensively in General Chemistry 1. So I do have videos up online, or you can ask me through email if you want more practice on how to do that. But here, aluminum solid goes to aluminum 3+, and to balance out our charge, we need 3 electrons. Now remember, when we want to combine half potentials, we have to make sure the number of electrons are the same on each side. So the common number of electrons I can get on each half equation will be 6. So I multiply the hydrogen by 3. I multiply the aluminum by 2 to get 6H plus 6 electrons goes to 3H2. 2 aluminum plus 2 Al3 plus goes to 6 electrons. Now I combine the equation, these two half equations, and that's my overall redox reaction. While B silver has a positive reduction potential, so it will not dissolve. Now, the E cell we've been calculating is energy, and we've also talked about earlier in this course delta G and K. These are also ways we can calculate energy in spontaneity. Therefore, all 3 of these are related in this triangle. So we have 3 equations, and we can use these equations to go from delta G to E cell to K, and K to delta G. So we can easily interconvert between these 3 equations. And note, from going to delta G to E cell, we have this term called F. F is a Faraday's constant, or Faraday's constant. It's just a constant. So it always has a number of 96,485. N is the number of electrons in the balanced redox reaction. So that's what N stands for. Now, for spontaneity, we have 3 different ways we can determine if a reaction is spontaneous or not now. So if delta G is negative, it's spontaneous. If E cell is positive, it's spontaneous. If K is greater than 1, it is spontaneous. So in problem 3, I give you reduction potentials. I want you to calculate delta G. So let's take a look at A. The first thing we need to do is determine what's being oxidized and what's being reduced. So lead 2+ is gaining 2 electrons to go to lead solid, so that is reduced, while magnesium is losing 2 electrons to go to magnesium 2+, that's oxidized. Lead's our cathode, magnesium's our anode. We can calculate E cell. E cell is 2.24 volts using our standard reduction potentials. Now that we have E cell, we can calculate delta G, because delta G equals negative NF E cell. The number of electrons in our balanced redox reaction is 2. We have 2 in each equation, so that's where N of 2 is coming from. Faraday is 96,485. E cell, we calculated, is 2.24. So delta G is negative 432,252 joules per mole, or negative 432.3 kilojoules per mole. Problem 4 is now calculating the equilibrium constant, and in A, for problem 4A, it's the same as 3A, so we already have delta G. And we have this equation that relates delta G and K. Delta G equals minus RT ln of K. So what I did was I rearranged stuff to get ln of K by itself, minus delta G divided by RT equals ln of K. Then I want to get K alone, so I need to get rid of the natural log. The way to get rid of a natural log is raise each side to the power of E. So K equals E raised to the power of minus delta G divided by RT. So minus delta G, so delta G is negative already, so minus delta G is positive 432,252, divided by R, gas constant, 8.314, and we're going to assume we're at 25C, so that's 298K. When you do this calculation, you should get your equilibrium constant is massive, 5.88 times 10 to the 75. The last thing we're going to look at is how to calculate these batteries under non-standard conditions. Remember, non-standard means we get a Q now. We're not at standard conditions. And all we have to do is slightly modify our equations to have this value of Q be relevant now. So let's look at how we can do this using the Nernst equation. So first we have a tin and manganese battery, and we want to calculate that under standard conditions. So tin is being reduced, manganese is being oxidized. So our battery has a value of 1.04 volts. So that's our E cell under standard condition. Now in B, we want we want E cell when tin is 0.01 and manganese is 2. Our Q is products over reactants. Mn2 plus is a product. Sn2 plus is our reactant. So this is 2 divided by 0.01, which is 200. So that's our Q. Alright, so we can calculate E cell now. So I'm going to use this equation right here, minus NF E cell. That's what we want. We want E cell. E cell not is under standard conditions. So that's what we calculated in A. So looking at our balanced reaction, we have 2 electrons. So minus 2, remember N is number of electrons, times the Faraday's constant, 96,485, times E cell, that's what we're calculating, equals minus 2, 96,485, times E cell under standard conditions, 1.04 from A, plus R, Gauss constant, 8.314, 298, we're going to say we're at 25C, multiplied by the natural log of Q, which is 200. When we solve this equation, we get a big number multiplied by E cell equals another big number. Get E cell alone, and we find E cell is 0.972 volts. And that is it for this video. If you have any questions about what we went over, please let me know. Otherwise, I'll see you in the next video.